Hello. In this video, I want to introduce a mathematical technique that is critical in statistical mechanics, the technique of Lagrange multipliers. This is a method for minimizing a function subject to some constraint. So before we begin, let's clarify what we mean by this statement. Let's start by considering the function with two arguments shown in the contour plot here. Pause the video for a moment and identify the minimum in this function for yourself. Hopefully you were able to work out that the minimum for this function is here. Now let's use the algebraic symbol f of x and y for this function. If we were at the minimum for this function, what would the following derivatives be equal to? Hopefully you know that at a minimum, all these derivatives would be equal to 0. Although strictly speaking, the last one of these, the grad of the function, is a two-dimensional vector of all zeros. Now consider the following pair of functions. In blue we have the function f of x and y, and in red we have the constraint g of x and y equals c. Where is the minimum value of the function f of x and y for which g of x and y is equal to c? Hopefully, you're able to work out that this point is here. We now cannot be in the true minimum of the function f of x and y, a point in the inner smaller contour, because at that point, g of x and y is not equal to c, so we would not be satisfying the constraint. Now my next question for you is, what do you think the arrows in this diagram represent? The arrows represent the direction in which the derivative, the vector that we obtain when we take the grad of the function, they represent the direction in which this vector points. The red arrow thus represents the grad of g, whilst the blue arrows represent the grad of f. Now notice something very interesting from this figure. At the constrained minimum, the point where f of x and y is minimized subject to the constraint that g of x and y is equal to c, the grad of f of x and y and the grad of g of x and y point in the same or opposite directions. In other words, the vector grad of f of x and y and the vector grad of g of x and y are either parallel or anti-parallel. This realization is the basis of the method of Lagrange multipliers. At the constrained optimum, we must have the following equality between the grad of the function f and the grad of the constraint g. We call the constant here, lambda, a Lagrange multiplier. The heart of the technique of Lagrange multipliers comes by rearranging this formula. We start by bringing everything over to the left-hand side and by thus setting the right-hand side equal to 0. We then remember that the derivative operator, the nabla symbol, the upside down triangle, has the distributive property, which allows us to write the following. In the final step, we then change the g of x and y into a g of x and y minus c, which we can do because we know that if we take the derivative of the constant c with respect to either x or y, we will get 0. Now the nice thing about all this is that we have turned a constrained optimization problem into an unconstrained optimization problem. In other words, to find our constrained optimum for our function f of x and y, we just need to solve an unconstrained optimization problem for the extended function f of x and y plus lambda times g of x and y minus c. Let's consider an example of how this is done in practice. The problem we are going to solve is shown here. We are going to find the optimum for the function f of x and y equals x squared plus y squared, subject to the constraint that 2x plus y is equal to 5. There are two steps in solving this problem. The first one of these is to construct the extended function F as shown here. For our example, the extended function is x squared plus y squared plus lambda multiplied by 2x plus y minus 5. We then differentiate the extended function with respect to x, y, and lambda, as all these partial derivatives of the extended function must be equal to 0 at the constrained optimum. If we do this for the problem here, we get the following expressions for the partial derivatives with respect to x and y. When these expressions are set to 0, they can both be rearranged so as to give us expressions for x and y in terms of lambda. When we take the derivative of the extended function with respect to lambda, we can thus rewrite it purely in terms of lambda as shown here. We can thus rearrange and find that lambda is equal to minus 2. If this is then substituted into the expressions obtained when the function was differentiated with respect to x and y, we get the values of x and y at our constrained optimum. For the problem shown here, we have that x equals 2 and y equals 1 at the constrained optimum. To summarize then, the method of Lagrange multipliers consists of two steps. In the first step, you construct an extended function. You then differentiate this extended function with respect to the arguments of the original function and with respect to the Lagrange multipliers. Because the arguments of f at the optimum of this extended function will be the same as the values of these quantities at the constrained optimum of small f. This technique is extremely useful in statistical mechanics and is also used in quantum mechanics. We will use it in subsequent videos in order to derive an expression for the generalized partition theorem. Consequently, please ensure that you have understood this technique and that you have tried some example problems involving this technique before moving on. Thank you for your attention.